everybody. In this video, we're going to talk about proofs by induction, and I'm going to show you an example of how to write a proof by induction. So proofs by induction are most useful when you have a recursive pattern. So a recursive pattern is something where the next step in the pattern depends on the previous step in the pattern. That's what recursive means. So the purpose of a proof by induction is to be able to take a recursive pattern and find an explicit formula for it and prove that the recursive pattern really does equal the explicit formula. So an explicit formula is also going to describe the pattern, but it's going to describe it in a way where you don't have to know what the 99th term is to be able to figure out what the 100th term is. So that's the basic idea of the proof. And the first step in the proof is to write the recursive formula and the explicit formula that you think will give you the same results as the recursive formula. And then the two steps of writing out the proof once you've written your formula are to prove that the base case is true. And then you assume that the n minus 1th case is true, and you use that to prove that the nth case is true. So again, this is easier if you see it in practice. So let me show you kind of what that would look like. So again, I'm going to use this pattern that my dad sent out to our family texting thread. And this time I'm going to show that my method is equivalent to this other method that my sister found. So in her other method, she saw that the amount that is different between each term, so like to get from 3 to 15, you add 12, and to get from 15 to 35, you add 20, and then from 35 to 63, you add 28, and so on. What she noticed is that these numbers are increasing by 8 each time. So the way that you would get the 99 is you would add whatever 28 plus 8 is, which I think would be 36. And if you do 63 plus 36, you can see that that does give you 99. So my sister's pattern is an example of a recursive formula or a recursive pattern because it requires the last term to know what the next term is going to be. So our first step is we need to write out the recursive and explicit formulas for both my pattern and April's pattern. So in both of these cases, we're going to write out what the nth term is, which this is a common notation for writing out the terms of sequences. So I'm going to use that. So in my case, the nth term is always equal to 2 times the term number squared minus 1. And I talked a little bit more in detail about this on the equivalence formula video. So if you want to, you can go back and review that. But the basic idea is that for the first term, you would take the 1 and double it to get the 2, and then you square that and subtract 1. For the second term, you take the term number, multiply by 2, which gives you the 4, then you square that, subtract 1. Same thing with the third and the fourth and the fifth, because like say if you take the fourth one, if you double the number 4, you get 8, and then you square it and subtract 1. So this is an explicit formula because you could figure out what the 100th term is, and you don't need to know what the 99th term is in order to find out what the 100th term would be. You would just plug 100 into n. So you'd say like 2 times 100 is 200. Then you would square that, which I think would be 40,000, and then subtract 1. So the 100th term would be 3,999 if I did my math right. So my formula is an example of an explicit formula. Then April's formula is going to be a recursive formula because in April's formula, you always take the previous number and you start with that number for your calculation of what the next number will be. So the way that we write this is we say that it's the n minus 1th term. So the nth term is going to depend on whatever the value of the previous term is. So if n is 2, or well, actually, let's do if n is 3. So if n is 3 in this case, we would say that f of 3 equals f of 3 minus 1, which would be 2. And so basically what we're saying is to find out what the third term is, you're going to take the second term, which was 15, and you're going to do something to it. So in this case, we would add 20, but we're adding something different every time. So we need to figure out how to describe what this number is that we're adding um, in a more clear and concise way. But I wanted to kind of explain how the notation works here. So the n stands for the term number you're working on, and n minus 1 is the term right before that. Um, so now I need to write the formula that she observed, which is that 12 and 20 and 28 and 36 are all increasing by 8 every time. So if I'm increasing by 8 every time, I can think about that. I can say, okay, well, repeated addition of 8 is the same thing as multiplying by 8. So I'm going to see if I add 8 times my term number, what that does for me. So if I test this out, I would say, okay, well, my second term, so f of 2, would equal f of 1 plus 8 times 2. And if I simplify that, f1 was the first term, which is 3, plus 16. And that is not accurately representing my pattern because I want to be adding 12. So I say, okay, well, I still think that this idea of repeated addition of 8 should be some type of multiplication by 8. So maybe if I try one more sequence, like the third term, maybe that will help me figure out what's wrong with my formula. So I'll say, okay, well, my third term, according to my formula, would be the second term plus 8 times 3, which would be the second term is 15 plus 8 times 3 is 24. And now I think I see what might be wrong because this 12 is 4 less than 16 and the 20 is 4 less than 24. So I think if I were to write a minus 4 and add that to my formula, then that would accurately represent it because now I would have this minus 4, which would end up giving me, I guess actually I don't have to write it there. Could just write it here because 8 times 2 is 16 minus 4 would give me the 12. And 8 times 3 would be 24 minus 4 would give me the 20. And if I continue this pattern just to check and make sure it's accurately describing the pattern that April found, I'd say the fourth term is going to be the third term plus 8 times 4 minus 4. And 8 times 4 is 32. 32 minus 4 is 28. So I would have the third term, which was 35, plus 28. And that is what I would want to have to accurately communicate April's method. So this formula right here is a recursive formula. And you actually also have to include the first term. So you have to say the first term in this case equals 3. Because since the formula depends on the previous term, you need to know what term number you're starting with, or like what the value is of the term you're starting with. So these two together make the recursive formula that describes April's pattern. So now that I have a recursive formula and an explicit formula, now it's time to prove that these two formulas will create the same sequence. So now that I've written the recursive and the explicit formulas, which are represented here, so here's the recursive formula, here's the explicit formula, now I can state my conjecture more formally. So the way that I would state this is I would say the sequence found by the recursive formula where the first term is 3 and the nth term is the term right before it plus 8 times n minus 4, that sequence is equivalent to the sequence found by the explicit formula where the nth term is 2 times n, you square that number and subtract 1. So the idea of a proof by induction is you first prove that the base case is true. And the base case is always really easy to prove because it's just showing that the first term in each sequence really is equal to each other. Then after we prove the base case, then we'll use the induction step, which I'll explain more on the next slide. But for the base case, we basically just say, okay, for the first sequence, the first term is defined to be 3. So that's the first term. In the second formula, in the explicit formula, the first term is defined to be 2 times the 1, because it's the first term. Then you square that and minus 1, which means that if we simplify this, 2 times 1 is 2. Then when you square that, that gives you 4. And 4 minus 1 does give you the result of the first term being 3. And so since the recursive formula and the explicit formula give you the same result for the first term, that means that you've proven your base case. So the base case is really easy. You just prove that the first term in each sequence is equal to each other. And then for the induction step, the idea is that you're going to assume that your conjecture is true for the n minus 1th term. And then using that assumption, you're going to prove that the nth term will always be equal between these two formulas. So basically what I'm doing in this case is I'm going to assume that the n minus 1th term is going to be equal to 2 times n minus 1 squared minus 1. So that's the assumption that I'm making. And then with that assumption, I'm going to show that the recursive formula really does generate this explicit formula. So what that would look like is I assume that the n minus 1 term does follow this explicit formula rule. Then I'm going to say, okay, well, by definition, the recursive formula tells me that the nth term is going to be the n minus 1th term, which I just assumed is 2 times n minus 1 squared minus 1. Then I take that n minus 1th term and I add 8n and subtract 4 from it. And now I'm going to simplify this to show that this really is equal to 2n squared minus 1. And I just do this by using algebra to simplify it. So first of all, I'll simplify inside of my parentheses and I'll say, well, 2 times n minus 1 by the distributive property is going to be 2n minus 2. And that number is squared, and I still have the minus 1 plus 8n minus 4. So I'm just simplifying this expression. And if I square 2n minus 1 times itself twice, I'm going to do this up here out of the way because I'm running out of room a little bit. But in your proof, you would actually show this as part of your proof. But if I multiply that by itself twice, 2n times 2n gives me 4n squared. 2n times negative 2 gives me negative 4n. Negative 2 times 2 gives me negative 4n. And negative 2 times negative 2 gives me positive 4. So basically that number squared ends up giving me 4n squared minus 4n plus 4 minus, whoops, I'll color code these so it's clearer to see. Then I still have this minus 1 plus 8n minus 4 for the nth term. And now that I have all of my parentheses taken care of, now I can go through and combine like terms. And I can say, okay, well, negative 4n plus another negative 4n is going to give me negative 8n. And when I add this positive 8n, that ends up giving me 0n. So all of the n terms end up canceling each other out. Then if I do positive 4 minus 1, that's 3. And then 3 minus 4 gives me negative 1. Or probably it actually would have been easier to do positive 4 plus negative 4 is 0, and then subtract 1. But in any case, what this ends up simplifying to is that the nth term equals 4n squared minus 1, which we actually showed this in the other video as well, that this is equal to 2n squared minus 1. And in a proof by induction, ultimately you're trying to prove that f of n equals this. So you would just use factoring and you would say, okay, well, 4n squared is the same thing as 2n times 2n minus 1. And then your last step would be to show that that equals 2n squared minus 1. And since you've proven that the assumption that the n minus 1th term follows this pattern implies that the recursive formula, when you simplify it, equals the explicit formula, this tells us that these two formulas are equal to each other regardless of what n is. And kind of the idea behind this is that the recursive formula requires the term right before it. So, like the 100th term requires you to know the 99th term, which requires you to know the 98th term, which requires you to know the 97th, and so on, all the way back until the first term. So the idea of the induction step is that once the base case is proved, if you can assume for any term number that the term right before it equals the explicit formula, that the result of the recursive formula will give you the explicit formula for the nth term, then I don't know exactly how to put it into words, but it's kind of like it's like an infinite proof, sort of, because it's like saying for any term right before the term you're looking for, if it's true for that one, and that implies that it's true for the next one, then the fact that you proved the base case kind of ripples forward and it proves it for any term number all the way out to infinity. That probably wasn't the most precise way to explain that, but that's kind of the idea of a proof by induction. And the two steps that you need to do a proof by induction are to prove that the first term of both formulas are equal to each other, and then prove that if you take the assumption that the n minus 1th term follows the explicit formula rule, then the recursive formula will create the same expression for the nth term. So if you have any questions about how to write a proof by induction, I'm happy to help you with it, but hopefully this gave you a good introduction to it. And I will also type out an example of this so you can see what a finished and polished proof by induction looks like. So thank you so much for your time, and I hope you have a good day.